So I recall, so last time we ended up with the definition of rank 1 convexity. And so W goes from R m times D to R is rank 1 convex. If for every lambda between 0 and 1, if we want, and for every A and B matrices, M times D, such that the rank of A minus B is smaller or equal than 1, W lambda A plus 1 minus lambda B is smaller or equal than lambda W at A plus 1 minus lambda W at B. Yeah, so this in particular means that these functions are separately convex. So separate convexity means you fix all but one component, and then you look at W as a function of this one component. So this is like convexity along Cartesian axis. So convexity implies separate convexity. And so, you know, we know that if W is smooth, we can look at a function. Oh, maybe we don't speak about smooth. So look at a function T assign W A plus T times A O times B. So this function has to be convex because I start from a point A and I go in the direction of a rank 1 matrix, because A, B, this always creates a rank 1 matrix, and every rank 1 matrix can be written in this form. It's just a little algebraic lemma. So in particular, if you take A and B, that in this matrix you only have one component, non-zero. So maybe 1 and then all are zeros and so on. And this is typically a rank 1 matrix. So this tells you that it's convex along the axis which corresponds to the element 1, 1 here. So maybe this was point 1, and the point 2 would be that if W is C2 on matrices, then you can differentiate this relationship. So you write this as a function of T for given A and given little a and little b. You calculate the second derivative, and because it's a convex function, it has to be non-negative, the second derivative. So this tells you that the second derivative of W at the point A, E A I J D A K L, AI, BJ, AK, BL has to be non-negative for every A matrix and every A and B. So A belongs to Rm and B belongs to Rd. So if you have a smooth function, you can check rank 1 convexity by calculating the second differential, Hessian, and evaluate it at these things, and you see whether this is positive or zero. So this condition is called Legendre-Hadamard condition. Let me call it star for simplicity. And it corresponds to the ellipticity condition if you look at your functional, which has a W over gradient as an integrand, and then you calculate the Euler-Lagrange equations, then this tells you something about the ellipticity of the equations. So this is a good condition to have a look. If you have a smooth function, but what we see here that the arguments have to differ by a rank 1 matrix, but sometimes you can get something more general. So let's have a look at the following example. So I take this just example. So you take A, which is just 1, 0, 0, 1 matrix. This is here. Then you go here, and this is B, and this will be 1, 0, 0, 3. You take a middle point, you call it C. So this is C, this is A, and this is B. And C is the middle, so it's 1, 0, 0, 0, 2. And now you go a little bit here, and you take D, which is 3, D is 3, 0, 0, 2. So you make a line like to D, and then you take E. This is the last one, and this is again the middle. So the middle is 2, 0, 2, 2. So we have these matrices here. And so what we see immediately is that if you look at E, and so assume W rank 1 convex, then W at E is smaller or equal than 1/2 W at D plus 1/2 W at C. And if you look at C, so we know that W at C is smaller or equal than 1/2 W of A plus 1/2 W of B. But if I want to plug it to the first inequality, I need half of W at C, so I take 1/2, and then I take 4 here, and then I take 4 here. So now if you plug everything together, then you get that W at E is smaller or equal than W, half of the W at D, plus 1/4 W of A plus 1/4 W of B. For every rank 1 convex function. And so in particular, what we see that matrices which are involved only A and B are rank 1 connected, so there is a difference with rank 1 matrix, while D is not rank 1 connected to any of those. So rank of D minus A is the same like the rank of D minus B, and this is 2. So you can also generalize this condition to get some richer spectrum of matrices to be involved, and you still have the inequality to be true for every rank 1 convex function. So this looks like a nice idea. So sometimes, at least in the book by Da Corona, it's called HN condition. So HN condition. And this can be formally written, but the idea is that you take your matrix E here, as we have it here, you decompose it, you take it as an average of 2 matrices, which were here, this was C and D. So these two are rank 1 connected. You take C, and you again take a line where the endpoints are rank 1 connected matrices, and they have at some point of the line there is C. So this was our A and B. So here is always rank 1 connection between the leaves on one floor, say, of this binary tree. And you can do this again, and you can do this again and again, and you go to infinity. And then you always have a coefficient lambda here, you have maybe lambda 1 here, lambda 2 here, and and so on. So these numbers are always between 0 and 1 because they just tell you what's the position of your matrix on this line segment. But at the end of the day, you can say, if you stop somewhere, that this inequality is satisfied for every rank 1 convex function. So f at E is always smaller or equal than, and now you have to multiply these weights to get the right inequality. And then these two are always rank 1 connected, but this one and this one, they don't have to be. So you have a rich set of matrices where only some of them are rank 1 connected. So with this, we can ask the following question. Because I think it's called, I don't know why H, but N means you go to the nth floor, say. So this is the 0 floor, that's the ground floor. This is the first floor, second floor, and so on. So now the question. So here, here at least some matrices were rank 1 connected. But now let's take matrices which are not rank 1 connected at all to each other. And I did a calculation. So I have exact values for you. So assume that W, again from, now let me do it 2 times 2 to R, is rank 1 convex, and it's even worse, it's non-negative. And assume further, let's further, W at A equals W of B, this is W of C, and this is W of D, is 0, where, and now comes the calculation, so where A equals, these are diagonal matrices, so minus 3, 0, 0, 1, B is minus 1, 0, 0, minus 3, C is 3, 0, 0, minus 1, and finally D is 1, 0, 0, 3. So we have the function and 4 matrices. And the question which we ask, is it possible that W of F is positive if F is not A, B, C, or D? So if I haven't done any mistake, then what we see that there are no matrices that would be rank 1 connected pairwise. So the hope, at least the hope, so we see that rank of A minus B is 2, and the same holds for A minus C, A minus D, and so on. So now, this is, matrices which are not rank 1 connected, so it's still possible like that we have a function such that it's always positive unless you are touching the points here. Surprisingly, it's not possible. And it's a result which I think the first people who did it was Aumann and Hart in '86, and they have this is some economic journal. They speak about probability, martingales, and biconvex functions. So a function is biconvex if it's separately convex in 2 components. So, and then there are many other people. So Casario Tarabuzzi. So no connection to the calculus of variation, the first paper, but the result was then taken by Calcvar people to do this. Then also Tartar. then Sekeli-Hidi, and also in the context of linearized elasticity, also Chenchian, Lemmer-Kemper. So many people have worked, so this is like a, and so let's make a picture of this situation. So because these matrices are just diagonal matrices, I can put them to the plane with x and y, where x is this component and y is this component. So this is x and this is y. And we have a picture like this. So I take something which should look like a square. And then A should be here. Then D should be here. Here we have C. And here we have what remains is B. So this is the picture of the geometric position of the matrices if I just look at the diagonal components, and this is x and this is y. And in this picture, if two matrices are rank 1 connected, they have to be either on a vertical line or on a horizontal line. Because if you have just diagonal matrices, then rank 1 connection means that the one component is the same for both. So that's the picture. You mean, is there, no, there shouldn't be any arrow. This was just a point. Sorry. Yeah, no, so they are not in the corners. They are, oh, sorry, these are really on these limbs. So they are not here, because if they would be here, then there would be rank 1 connection. So this is like a window, but there are these limbs going like, it looks a little bit like a mill. No. So now we want to show that this is not possible. So there is a question mark missing. And so to show that this is not possible, we use these corners, as Katarina mentioned, and we put here A prime. And I put here D prime. So D prime will be the corner, the primes are the corners. Here that would be B prime, and what remains is C prime. So these are the corners. And now the situation is better because C prime and B prime are rank 1 connected. And my hope was to make it in such a way that D prime is in the, it doesn't look like from the picture, but from the matrices, the D should be in the middle of those, between these two. So now we have W rank 1 convex, and so we say, we look at A prime here. A prime, and we say W at A prime is smaller or equal than 1/2. This is the coefficient, so I would say that the distance here is the same like the distance here. So 1/2 is just my choice. This could be also different, but then the calculation is more involved. W at A plus 1/2 W, and what do we have here? D prime. So now we are here with D prime. So we use convexity again here, and we estimate the value at D prime by the value at D and C prime. So I can do it, but I mean, I already would estimate, because here I have D prime with 1/2, so I already estimate this value. And this will be 1/4 of W at D plus 1/4 of the W at C prime. So there is no trick. You can also multiply by, you divide by 1/2 and then you get the thing here. Oh. So now we have, these are the original points. These are the prime points. So in each step we get rid of one of the prime points because these are artificial and they do not belong to our setting. So we do, there was 1/2, so I do 1/4 of W at C prime. And this is smaller or equal, so look at the picture C prime. This is B prime and C. So it's 1/4 of W at C and 1/8. Was it 1/8? Yeah, I think it's 1/8. And plus 1/8 W, and then we have C and B prime. And finally, I get that 1/8 of W at B prime is smaller or equal than 1/16 W of B, because B prime is again here, and 1/16 W of A prime. So what you do now with these inequalities is that you plug the second one to the first one. You replace this term by this estimate. Keep D and replace the estimate for W at C prime by this estimate. And then you are here for the B prime. At the end you get W at A prime, and then you have something, so you have A, B, C, D, and A prime again. A smaller coefficient. Here is 1, here is 1/16. So the circle closes in a way. And so, because I have on the right hand side 1/16, I subtract it and I get 15/16 here as a coefficient. So 15/16 of W at A prime is smaller or equal than 1/2 W of A plus, now it's really involved, 1/4 W of B plus 1/8 W of C plus 1/16 W of B. I, B, C, D. So is B here? B. Aha. Thank you, Ulisse, because you are right. B, yeah. So now you multiply this guy by 16/15 to get 1 here as a coefficient. And that's it. So then you get some coefficients which are a bit better. but you can imagine that you get W of A prime is more or equal than something, and now, I mean, it's times 16, so it's 8 over 15. And now we take 4 over 15 plus 2 over 15 W of C plus 1 over 15 W of B. So now the final check is 8 plus 4 is 12, 14, 15. So good. So we have the sum of the coefficients is 1. So these are coefficients of convex combinations. So if the function is 0 here, 0 here, 0 here, 0 here, inevitably, as a non-negative function, it has to be 0 at A prime. So the function has to be also 0 here. So maybe I can use colorful chalk. So the function has to be 0 here at A prime. Now you do the same procedure again, but you don't start at A prime, but you start at D prime. And it tells you that, again, the function has to be also 0 here. Again, you start with C prime and see that the function has to be 0 here. And finally, you show that it also has to be 0 here. And this is not enough, because suddenly what you see is that these 2 points are rank 1 connected. So if the function is 0 here and 0 here, it has to be also 0 on the whole piece, but also here, because D and C prime are rank 1 connected. So the function has to be 0 here. For the same reason, it has to be 0 here, and it has to be 0 here, and it has to be 0 here. And at the end, you take point here, which are on the horizontal line. They are rank 1 connected, so you again show that, in fact, the function has to be 0 also inside this square. So there is no way how you can have a function which would be 0 only at these 4 matrices, and this function would be rank 1 convex. Because this has to be also 0 at this window and these limbs. So if you have a convex function which is 0 on these matrices, then it would be inevitably 0 on the convex hull of those matrices, which would be something like this. But for rank 1 convexity, because it's a weaker notion, so the hull is smaller, because you have more functions to test. So this is really a nice, and this configuration is called, in the calculus of variation literature, T4 configuration. And I'm not sure, but I think the T comes from Tartar, because sometimes people also call it Tartar square. So that's a nice construction. And I mean, these people, also have it in the paper, and then Casadio Tarabuzzi has a paper on sort of algebraic characterization of quasi-convexity. And in the process of developing the paper, he discovered this case or rediscovered this case and so on. So you can... Now, sometimes we consider that some functions can take values plus infinity also. So we can say, how about if my rank 1 convex function is allowed to take a function plus infinity? So before that, we just noticed that because it's separately convex and it's separately convex, so it means that it's already continuous because the separately convex functions, which are finite valued, are continuous. So this means that we have a continuous function here, and however, if W takes and I add plus infinity, then what I want to say is that then you can have a function which has these properties. Because you just take, then we can take W of F equals, and then this is 0 if F equals ABC and D, and plus infinity otherwise. And this function is rank 1 convex. These are not rank 1 connected, so there is no line in between them, so the function is plus infinity. So that's a big difference. Going from functions which take value plus infinity or continuous functions, it's a big difference in this setting. So all notions we had up to now, so we have convexity, convex functions, we have polyconvex functions, and we have quasi-convex, and we also have rank 1 convex. Then all these are cones of functions. Convex cones. You take two convex functions, you add them, you get again a convex function. You multiply a convex function by a positive number, you again get a convex function. And the same holds for other notions of convexity. So these are cones or convex cones, that's important. And if you have convex cones, you can of functions, you can also have a look at corresponding measures. So if you have a function which is convex on some compact set, say, so you take a probability measure which sits on this set, and the value of the function at the barycenter must be bounded by the integral of f with respect to this measure. So this brings you into the game say subsets of probability measures. So you can look at, sorry, on a compact set. On a compact set in R m times d. So it's a finite dimensional, so it's closed and bounded. So then you know that W at nu bar, this is the barycenter of the measure, must be smaller or equal than the integral, let me say, on a compact set capital K, W F d nu. So this is if W is convex. Now, if I want to have this inequality for rank 1 convex functions, this is a set which is larger, I have more rank 1 convex functions, then I know I have to take smaller set of measures. If let me call it star star because we already had star. If star star, this is this Jensen inequality. If star star holds for every W rank 1 convex, then we call nu a laminate. So while here, this was just the convex cone of probability measures, here we have a special subset of measures which are called laminates. So these measures are called laminates. If this Jensen inequality holds for every W quasi-convex, then we call nu a gradient measure. Sometimes people say Young measure. You can also have the same thing for polyconvex, but there is no name for polyconvexity. But again, it gives you, so convex hull is the largest set, then this is because this is the all probability measures. And if you go to more and more general notions of convexity, you get smaller and smaller set. So what do we see here, for example? I mean, if I take a point here, if I take a probability measure, which would be supported on A, B, C, and D, and would be such that the barycenter, the first moment would be here, then I know it's in the convex hull. So for every convex function, 0 at these points, the value of this convex function here would be smaller or would be again 0. But I see that this point doesn't belong to the rank 1 convex hull, or the rank 1. It's not a laminate, because laminates have barycenters only here in this red piece. So the same story, like you have the for convex function, like sort of Hahn-Banach theorem, extreme points, and so on. You can play this game for these other notions of convexity in kind of more general setting. And this is also related to the Choquet theory and boundary integrals and so on some measures, but it's quite complicated. But I mean, this is developed in some other areas of mathematics, not in the calculus of variations, but we can borrow this from this area of mathematics. So maybe now I erase the board and then we go on with some examples. I mean, no, you may, yeah. So this will be maybe on Wednesday, if not on Monday. That sometimes you need to do, if you have a problem, a variational problem where the integrand, depending on the gradient, is not polyconvex, it's not quasi-convex. So then you cannot really show that there is existence, and there might be no existence. And there is a technology which is called relaxation. So you look for some sort of gamma convergence and a lower semi-continuous envelope of your problem. And in this business, this is important to know where my lower semi-continuous envelope would be 0, for example. So you mean this one or yeah? F? No, I say the question is I have a function which is 0 only at those matrices, it's non-negative, so 0 is the minimal value. And the question was, is there a rank 1 convex function which would be positive otherwise? And this was to show that it's not possible. Because inevitably, every rank 1 convex function, which is 0 here, 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 and here, also has to be 0 on this red or pink part. I mean, it might be, yeah, but definitely it has to be 0 here, but yeah. I mean, you know what? I mean, because we are speaking about laminates and probability measures, you can also define something which is called, like you have a convex hull of a set, and you have a rank 1 convex hull of a set. And this is exactly the rank 1 convex hull of those matrices. So if you take a distance function from the original 4 points, so I take a distance function, so Euclidean distance from the 4 points, and this will be my new function. So given a function, I look at the Euclidean distance to my set ABCD, and then I calculate, say, the largest rank 1 convex function, which is below this given function, which is not rank 1 convex. Then I get a function which is 0 exactly on this pink picture, and it's positive otherwise. So the function is positive otherwise. So there is a function which is 0 only here and positive otherwise. Some other question? I'm happy that you ask because this means you think about it. Oh no, so I erase it. By the way, Aumann got a Nobel Prize for economy. So I forgot to tell you. So now we will again go back to quasi convexity. So let me recall the W of A is to be smaller or equal than 1 over the measure of omega. Let me put phi here today. For every phi, which is W1 infinity 0 on the boundary, omega R M, if and we assume that omega is in RD, it's bounded, dipshits. And A is arbitrary point. So this is the definition of quasi-convexity. And we know that W continuous means that the quasi-convexity implies rank 1 convexity. So W quasi-convex implies W rank 1 convex. And this is good. So let me maybe write here that W was supposed to be a matrix function working on matrices M times D to R. So this was the assumption which should go here. And then we have this. How about if W can take a function plus infinity, then the picture is different. If W is from M times D to R, then quasi convexity doesn't imply rank 1 convexity. And this can be done by the example, which is very similar to what we had before. And so you take W of F to be 0 if F equals A or F equals B, and rank A minus B is bigger than 1, and plus infinity otherwise. Plus infinity otherwise. So this function is not rank 1 convex. And no, I think I have to take No, I think this is want to have a function which is quasi convex, not rank 1. No, rank NAB. Yeah, rank NAB has to be 1. I'm sorry. So this function is not rank 1 convex because in the middle of your line segment A and B, you are plus infinity. But it's trivially quasi-convex. So quasi-convexity, as I said, is a difficult property to verify because you have to check this inequality, and this is difficult. So we don't have really many examples of quasi-convex functions which are not polyconvex. So when in 1952 Meyers proved his result about necessity quasi-convexity, in fact there was no polyconvexity yet because this came later. So he, in fact, developed some example like using these determinants and so on, but there were just convex functions, and everything had to be developed from that because there were really no good examples. So now it's better. but still it's a quite mysterious condition. So the example which covers all conditions of convexity was given in 1992 by Hilbert and Da Coruña. It's an ARMA paper, and it's a function which is defined on 2 times 2 matrices, so the simplest case. So, and this function is called in their setting F gamma, and this depends on A. This is the matrix, and this is defined like that. You take the Frobenius norm, put it to the power 2, and multiply by this number the following bracket, which is 2 gamma determinant of A. A is in R2 times 2, and this norm squared is a sum of Aij to the power 2. So Frobenius norm. And now what they proved by mostly brute force calculation is that F gamma is convex if and only if gamma is smaller or equal than 2/3 of square root of 2. Now, because we are talking about particular values of gamma, it is important to know which norm you take. Now, the point 2 is that F gamma is polyconvex if and only if the modulus of gamma is smaller or equal than 1. So if you forget this term and look at it and you see gamma is smaller or equal than 1, then you see that this function in fact is non-negative, because this is this Hadamard inequality between matrix norm and the determinant. And if you take the Frobenius norm in 2 dimensions, it's exactly 2. Now comes the interesting part. Now, quasi-convexity. So the claim is the following. There exists epsilon positive such that F gamma is quasi-convex if the modulus of gamma is smaller than or equal than 1 plus epsilon. And the last point says F gamma is rank 1 convex if the modulus of gamma is bounded from above by 2 over square root of 3. No? So this looks like, so what we see that convexity this is a number which is smaller than 1. So you have polyconvex, I mean, if gamma is strictly between 1 and this number, you know that the function is polyconvex but not convex. Now you know that if you are here, then the function is rank 1 convex. What is not clear is what's the value of this epsilon. So the result only says there is epsilon positive, which means, so we know the maximum value of possible epsilon is this number minus 1. Because if the function is not rank 1 convex, it cannot be quasi-convex. So, but we don't know whether, so the question which is open is epsilon equal 2 over square root of 3 minus 1. I mean, you know what? So, of course, there are numerical experiments. In fact, even there is a old paper by Da Coruña and Heberle, I think it was his student, so when they did lots of numerics on that. And it's not really clear, I mean. So, this function is very good because, I mean, I haven't talked about it, but in elasticity, we typically need functions which are frame invariant. So whenever you multiply your argument by rotation from the left, you assume that you have the same value. And this would be this. This would be this. This function satisfies this. It's a polynomial. It's for homogeneous. So for example, if the function is not quasi-convex at 0, and you evaluate the integral on the right-hand side, it would go immediately to minus infinity. Because if it's negative somewhere, then you multiply it by a constant, and then you go down. So it would be clear numerical proof, say, because suddenly you know, it's not like that it's 0, 0, 0 something, and you can say this is a numerical error. It would really, you know, go down. So, but this is very much related to the following question, which it's still unsolved, and that's why I'm decided to talk about it on Friday, because then you have a weekend. And if I don't see you on Monday, I know that you solved it and you are in Princeton already or somewhere. So it was a long-standing question whether rank 1 convexity implies quasi-convexity. So we know the other, because I mean that's a kind of nice condition. You can check it. It looks like convexity almost, and so on. So if I give you a function, you have this second derivative, Legendre-Hadamard condition. So you can really work on this a lot. And in fact, I would say the rank 1 convexity is traced in late 30s by in the work by Terpstra. And then Morey came 52, and then this quasi-convexity condition. And then he claimed, or it was a conjecture, that it's the same like rank 1 convexity. And then later in his book, I think this was 56 or 55, and so the paper was 52, then later book, I think he was not sure too about this conjecture anymore. And so this was a big problem in the calculus of variation. Is quasi-convexity the same like rank 1 convexity? And so this goes to your question. So there were many numerical experiments. So there were kind of examples of rank 1 convex functions created, and people were trying to minimize numerically and solve the problem. Of course, you cannot prove anything. You only can come up with the counterexample numerically. But it was in fact open for 40 years. And in 1992, so the question was, is this one, but more general question, does rank 1 convexity imply quasi-convexity? So the partial answer which I will give you is no. In the dimensions, if we are in R m times d. And a question mark. So it's no if D is at least 2, Mn is at least 3. There is an easy case, is M or D is 1, because then quasi convexity is convexity, and rank 1 convexity is also convexity, because if you have a row, if you have just a row vector or a column vector, and this is your matrix n times 1 or 1 times m, then everything is rank 1 connected. So we are interested in the case where so know if this holds, and yes, if the minimum of M or D equal 1. So what remains is the case that M equals 2 and D is arbitrary, and this is open. And I will show you the Schwerach's example because it's very easy to show, and it's a beautiful example. So this is easy, and this will be the example. So this is Vladimir Schwerach in 1992. There is a paper in Proceedings of the Royal Society of Edinburgh. So maybe at some point we will make a break again, but maybe it's too early. So maybe about 11 we can do a little break if you want. So we can open the window. What's the quality of the air? 700, yeah. So the quality is 700. So is it what? You want to open the window? Yeah, it's open. Oh, it's open. Aha. It's not seen here or felt here. So Schwerach's counterexample. So it's a Czech guy, so I use all these accents, but you can. So he is working in the case D equals 2 and M equals 3. And then so it's a case when you have a domain which is 2-dimensional, and then you have a map phi which has 3 components. So as I said, before him, somehow, many people try to construct a rank 1 convex function and to check this inequality numerically, say, or somehow. He took a different way. He started from the deformation phi and constructed the function to it. So, and we will also use this other notion of quasi convexity, or the equivalent formulation that you use these periodic functions on the domain, on the square domain, because it's easier. So you take, we will have P of X will be the following vector. So it will be 1 over 2 pi, and you take sine of x1, you take sine of x2. Oh, but sorry, it should be 2 pi x1, 2 pi x2, because I want to have it one periodic. So I multiply by 2 pi, but I also divide by 2 pi because at some point we will need to calculate the gradient. And then the last component will be sine of 2 pi x1 plus x2. Now, X belongs to the unit square, and we have 3 components. So now we go for the gradient, which will be needed. So to calculate the gradient in public, this is something what you should never do, but here it's easy. So we get, this is a matrix, which will have 3 rows and 2 columns. So it will be cosine of 2 pi x1 and 0 here. It will be 0 here and cosine of 2 pi x2. And the last one will be cosine of 2 pi x1 plus x2 and cosine of 2 pi x1 plus x2. Huh? So this is the gradient. So now I take a subspace of the matrices in 3 times 2, and this will be the following subspace. So this will be a matrix F will be there. Such that there exist R as T, real numbers, R as T, real numbers, such that F is simply R00 as T and T. So it's a subspace of matrices which have this structure. So what we can do now, we say, and what we see is that the gradient of phi lives in this subspace for every x. So now we take a function g only on this subspace. That's the step 1. We construct a function which is living only on this subspace. And this function g, so because it's on the subspace, I will put the arguments r and s and t. And this is nothing else than minus r times s times t. Huh? Oh, that's the function. So now look at this function on this subspace. So this subspace is interesting because if you look at it, so you say, I am in this subspace and I want to go in a rank 1 direction from a given matrix R0, S0, T0. So what are the possibilities? If here you want to have a rank 1 matrix, it means at least 2 of the coefficients have to be 0. Because if T is 0, but R and S not, then you have a invertible matrix here. And if S and T are non-zero, then you have a matrix here which has a non-zero determinant, and it's the same if S, and so only R and T are non-zero. So somehow there are only very few rank 1 directions. If I stay somewhere and I want to go in this subspace in the rank 1 direction, then I don't have many possibilities. It means 2 of the values of R, S, and T have to be 0 at least. So maybe I go here. If we if we take F in L and to go from F in a rank 1 direction, we don't have many possibilities. We only have the following choices. So you either go in 1, 0, 0, 0, 0, 0, or you go at 0, 0, 0, 1, 0, 0, or you go at 0, 0, 0, 0, 1, 1. Huh? And if you go in these directions, means 2 of them are 0, so then this function is not only rank 1 convex, but even rank 1 affine, which means also, if I forget this minus, then this is a rank 1 convex function. Like you have affine functions are those that f and minus f is rank 1 is convex, so you can do it. So on this subspace, this function is even rank 1 affine. So G is rank 1 affine, meaning that plus minus G is rank 1 convex. On L. Remember that we are still only on the subspace. But because my gradient is living on the subspace, I can also check this inequality for this particular test function phi. So what we can calculate, so now we are interested in the following problem. So we take the 0, 1 to the power 2, and we take G of gradient of phi x dx. So this means I'm interested in quasi convexity at 0. So A is 0, and I forget A, and I have just the gradient there. So I want to calculate this. So this is the integral of 0, 1 to the power 2, and then I put minus here. This is this minus, and then I have cosine of 2 pi x1 times cosine of 2 pi x2 times cosine of 2 pi x1 plus x2 dx. So now you go back in your mind and to the high school class when you remember these formulas for cosine of sum. And I think you just use the formula that cosine of alpha plus beta is cosine alpha cosine beta, and I think it's minus sine alpha sine beta. It should be like that because I know that cosine of 2 alpha is cosine squared minus sine squared. So this is the Sherlock Holmes quick test. Doesn't prove anything, but gives you a better feeling. So now if you do this here, So you get these two terms, it's cosine. So if there is nothing like that, then this would disappear because it's a periodic and it's x1, x2. But the first term gives you, because of this formula, the first term gives you also cosine x1 and cosine x2. So there is a term which is minus 0, 1 integral of cosine squared 2p x1 cosine squared 2 pi x2 from the first term. And there is another term which will be plus 0, 1 to the power 2, and then we have cosine 2 pi x1 cosine 2 pi x2 sine 2 pi x1 sine 2 pi x2 dx. And I think this vanishes because everything is periodic and somehow. So this guy is 0, but this guy has a minus and there is square and square. So this number at the end is smaller than 0. So somewhat it shows that if I restrict my matrices only to this L, then this function is not quasi-convex. But the point is now that we have to have a real proof, we need to extend it to the space of matrices, not all from L. So this is good to know. And now we need to extend G from L to the full space. So in this case, it's 3 times 2. And it's not clear whether this is possible. But we know that there is a modification of G that allows you to do the extension. And so the modification is the following. You take G of F plus some little epsilon, and then you put here F to the power 2 plus F to the power 4. And you take epsilon small. So, I mean, I only added a convex terms, so I couldn't make it verse, you know, so, and still, if you do the same calculation, so epsilon positive and small, so still I have that, I'm still remaining on the subspace, but this function is also rank 1 convex on the subspace, but it's not quasi-convex on the subspace. Because, you know, these functions, cosine and sine, they are always bounded, and so if you take epsilon small, then you add the norm of the gradients, but, you know, this is negative, so I can add a bit and still remain negative. So this G, maybe I call it G epsilon because it's a new function. And it's obvious that G epsilon is rank 1 affine, is rank 1 affine. No, now not affine because this is not affine, but it's rank 1 convex on L, but not quasi-convex. Yeah, sorry. So this should be written like, so this will be my G epsilon of F. You are right. Thank you. So G epsilon is rank 1 convex on L, but not quasi-convex if epsilon is small enough. So now we define, and this already can be extended. So we define G epsilon K of F, and this will be G of PF plus epsilon F to the power 2 plus F to the power 4 plus K times F minus PF to the power 2. And what remains to say was PF. So PF is a projection of a general matrix on the subspace. So PF is given here. PF is, you take F11, 0, 0, F22, and then you take the average of the components. So you take F31 plus F32 divided by 2, and then you put here the same. So P takes a matrix in 3 times 2 and gives us something in L by this procedure. And now the claim is for every epsilon positive, there exists K positive depending on this epsilon, such that G epsilon K is rank 1 convex. Assume we prove this, then we would know that this function is not quasi-convex. Because this is the second part of the claim. Why? Simply because assume this is rank 1 convex, so you again show that the integral here G epsilon K gradient of dx. So this means, what is it? So I claim that this is smaller than 0. Why? So the first term, I don't have to do anything because this is already in the subspace, my gradient. So I don't have to project. Here I have these terms. We said this is possible to make epsilon small, that this is still negative. And the last term, because I'm in the subspace, this gives me 0. Because so f minus pf to the power 2. So the last term, independently of k, doesn't contribute. So this is because p grad phi is grad phi. So once you show that this is rank 1 convex, you are done. So now what you have to show is that it's rank 1 convex. And for that, because if you look at it, this is a polynomial of the, it's called quartic because it has the highest power is 4. It's a polynomial. So I do the proof of this rank 1 convexity, and maybe then we can take a 10-minute break because the air doesn't change too much from, yeah, you need to wave a bit. As I said, somehow to calculate derivatives in the public is dangerous. So I did the calculation at home and I will copy now. So the thing is that we use this Legendre-Adamard condition, and so we calculate the second derivative, and so the claim is as follows. So we do the contradiction. So assume that there exists epsilon positive such that for every k positive again, G epsilon and k is not rank 1 convex. So we calculate the second derivative. So it means that there exists fk and ak and bk. So I can consider that ak equals the norm of bk, and this is 1. Because if you do this convexity, you multiply by the t. You do f plus t times a, o times b. So the norm can be eaten by this t. Such that So for every k, I take these guys such that the second differential of G, epsilon, and k at the point fk, and then you take the directions are ako times bk, ako times bk is smaller than 0. So that's the contradiction argument. So now there is no way then you have to really evaluate this. And it should be like that. So in a general matrix, and if you go an x, so capital X is now, this will be AK, BK then. So this is the second derivative of G at PF in the direction of PX plus 2 epsilon x squared plus epsilon, maybe I go here, epsilon times 4f to the power 2 x to the power 2 plus 8 times f dot product with x to the power 2 plus k times x minus px to the power 2. And this is, so now if you look at it so that the function is coercive in f. So if I assume that taking, so this guy, so t squared g epsilon and k is coercive in f. So I can assume that my fk is bounded because this has to be, finally it will be smaller than 0. And it's coercive, so it has to be bounded, oh no, the set has to be bounded. So we assume that fk may be converging to some f bar because fk is bounded by a constant. So now what I see, if I take k larger, if I take k1 and k2 such that k2 is larger, then this second, this Hessian will be also larger, evaluated at x. So if you so how is it, dg epsilon k at f x is bigger than d squared g epsilon k f, no, not k, but j, if f and x if k is larger than j. If k is larger than j. So we can assume finally that this is, because this has to be negative for every k, so then I would know that this has to be negative. So at the end, I get that, so the square GPF at the point P, A, P, and PAB, where E, A, and B, maybe I put bars here again, if you want, because we have also F with bars. So here we, because we have this bound, we can also assume that AK converges to A bar and BK converges to B bar. So in the limit we have this plus 2 epsilon, because the norm is the norm is 1. I forget this term which is non-negative and this one. So if the whole thing is negative, then if I forget this term, it's also negative. So I put here plus k times k times A bar and this has to be smaller than 0 for every k, which means you have to be in the subspace L. This implies that PA bar so you are in the subspace, and on the subspace the function is rank 1 affine and so on. So this is the contradiction. So this is 0, and if this is 0, so this means epsilon is smaller than 0. So this means, this implies that epsilon is smaller than 0. Because the function was rank 1 affine, so this is 0, this is 0, and epsilon is here. So this is the contradiction. So it cannot be, and really there is epsilon such, for every epsilon there is k such that the function is rank 1 convex. So, I mean, Miller got a prize at the European Mathematical Congress for this positivity or high integrability of the determinant, and Schwera got the prize for this at the same congress. So you see, it's not so, I mean, it's just, you need a kind of high school mathematics to, maybe this was a little bit more involved, but the sine and cosine thing is something what you really can explain to a high school student. And so if you don't mind, I suggest we make a 10-minute break and then we go on. I'll switch on the, so there was a point, and it was a correct point. So the claim was that for every epsilon, there exists k positive such that this is rank 1 convex. There shouldn't be, but not quasi-convex, because it might be that if you take epsilon large, then finally you get function which is quasi-convex. On the other hand, this, for us, it's enough if we choose epsilon small. So, I mean, I made a little pause before I wrote this, but then I realized, oh, I was told that in fact this is true, this was not, so forget it. So the claim is like this: for every epsilon there exists k such that the function g epsilon k is rank 1 convex. And we know that if you take epsilon small and k large enough, then this is not quasi-convex. But so that's the, yeah, now we, so I didn't erase that, but now I should erase it, and so that's So now if I'm already here and there is some little space, so if you are in other dimensions, like that D is bigger than 2 and M is bigger than 3, or then you have a function which is defined on the larger matrices, but you define a function which only depends on this subspace of the matrix, 3 times 2. So you restrict your function to this, and then you do the same construction. If you are in a higher dimensional space, you take the same function G epsilon k, you only restrict it to this subspace. So that's the proof in general dimension. If D is at least 2 and M is at least 3. So after this proof was published, then of course people try to make it working also in 2 times 2 case, and it seems to be still open. Also, many people tried, and even there are some preprints on. So, but there is always some little trouble here or there, and so the question is open. So. Open question. Does rank 1 convexity imply quasi convexity if we work on R 2 times B. In fact, 2 times 2, but I mean, if you cannot prove 2 times 2 and you can prove 2 times 5, then this will be also fine. So, so that's the problem for the weekend. In particular, R 2 times 2. In it would be. Once I had a discussion at some conference with Bernard de Coruña, and I said, but this was a discussion, like I said, I think this is the same, and de Coruña said, it cannot be. And then we, separated. So somehow, it's like, it was a discussion like, I don't know. I mean, it's like before Schwerak, many people tried, and I mean, all these numerics look like that there is no, that it looks fine, that really there is a, and suddenly, you come up with something, so. It would be, I mean, so Schwerak's example is an example which is, we have it, it's good, but on the other hand, it's not frame indifferent. So maybe if you add rank 1 convexity and frame indifference, then it already, it's an extra property. But I think in some higher dimensions, there is a paper by Grabowski, and he has some also example in this high dimensional space where I think his function is sort of frame indifferent, but in non-physical dimensions, as far as I remember. And then many modifications of this Schwerak construction appear because, in fact, it's just maybe besides this Grabowski, this is the only sort of case that we have, and then we kind of modified and so on. So, if you if you look at other notions of convexity, so you, for example, you know that if you have a convex function, if f is convex, then and maybe f works from m times d to r, then f tilde, which goes from r d times m to r, and is defined like f tilde A is f of A transpose is also convex. Is convex. And the same holds for polyconvexity and rank 1 convexity, obviously. So if you have a polyconvex function, you can create a new one in this other space by taking a transposition. So, and there was a question by Giovanni Alberti whether this holds for quasi-convexity too. So let's have a look. So so the question is, how about if f is quasi-convex? So the answer is that you take a quasi-convex function, you do the transposition, and you get something non-quasi-convex. So for quasi-convexity, it doesn't hold. So this was a question by Giovanni Alberti. Maybe like 97 or something like that. And so we can try this now here. So the our choice would be, let's take f tilde of A, and this will be my epsilon k function at A transposed. In such, and I pick up epsilon and k in such a way that this function is rank 1 convex. And I want to show, and no, it's not quasi-convex. So pick up for epsilon and k such that G epsilon and k is rank 1 convex. And not quasi-convex. And this would be the goal, but we first start with taking, the first step would be, first we only consider the following. I take my f tilde of A, and this will be this is the first step. So maybe I just take f tilde A, this will be my G of A transposed if A transposed lives in the subspace L, and it will be plus infinity otherwise. So maybe let's call it double tilde if you want. So we just take this subspace L, we take a matrix which now A is in R 2 times 3, and we say it will be my G A transpose, or if I'm in L, and plus infinity otherwise. So then we know we see that F tilde tilde is rank 1 convex, because F tilde tilde of A equals minus RST if A is R0T 0ST and plus infinity otherwise. So if you take A that is not in this subspace L, and you move in the direction of a point from this subspace, then you are somewhere a little bit not in the subspace, so then you are plus infinity. And if you start in the subspace, then you remain in the subspace because it's a convex set. So and it's a subspace. So this function is rank 1 convex. While if you don't do the transposition, and if you are in the other dimension, so 3 times A, then this will be just this G, and we know that then this function is not quasi-convex, because I can also extend it by plus infinity to L. So we see that this is rank 1 convex. Moreover, G of A, which is defined like minus RST, if A equals R0T 0ST and plus infinity otherwise, so it belongs to L, and this belongs to L transpose. So G is not quasi-convex. By the proof before. So the question is, this is not quasi-convex, this is just the transposition. So the guess would be, this is rank 1 convex but not quasi-convex. And we have an example of a function which is on dimension 2 times something, and it's not quasi-convex. So this is the plan. To get a counterexample in this lower dimensional space through this. However, you look at what gradients are living in this subspace. For the Schwerak example, we had this phi, so it was the sine and cosine, or the cosine for the gradient, and it was very, very nice. But here, so what are functions P in W, say 1 infinity, 0, 1 periodic, if you want, 0, one periodic, but now q to the power cube, because we are working in the three-dimensional subspace, periodic from R to R2, such that gradient of phi lives in L transpose. So we have phi1 and phi2. We have phi1 depending on x1, x2, and x3. And then we have phi2 depends on x1 and x2 and x3. But we see from this, so R is here, so but there is 0. So phi1 shouldn't depend on x2. So and again the second component shouldn't depend on x1. The last component has to be the same. So they should be the same. So finally, from this condition, you get that phi1 of x1, x2, and x3 is A of x1 plus B of x3. And the second component, x1, x2, and x3, is C of x2 plus B of x3. You have to have this form of your phi. So now if you do this this gradient, so you get A prime, so the gradient of phi of x is in the right subspace, and it's A prime, 0 B prime, 0 C prime, B prime. So you do the calculation, 0, 1 to the power of 3. You take minus A prime, B prime, C prime, A prime of x1, B prime of x3, and C prime of x2, dx. What do we get here? Any guess? Because these guys are periodic. You have to have periodic functions because of periodicity. So this is bad because this doesn't give us any counterexample. So this is an example which also takes values plus infinity, that you may have so this function here is also quasi-convex. But the one with the transposition is not. So that shows the answer to Albert's question is negative, at least if you allow the function to take values plus infinity. Later, this example was modified to only finitely valued f by Stefan Miller around 99 or something like that. So finite valued, no finite. By Miller in maybe 1999. So this was the kind of so doesn't give us anything, unfortunately. On the other hand, assume for a while that in the case 2 times 2, it's the same. So let's dream for a moment. Let's dream that if we work on R 2 times 2, then this problem cannot happen, because if I assume this is the same, so I also transpose it and I get a rank 1 convex function. So somehow this means that if f from R 2 times 2 to R is rank 1 convex, then first f of A is more or equal than the integral over, say, 0, 1 to the power 2 f A plus grad phi of x dx for every phi which is, say, Lipschitz and 0 boundary conditions. But also that f of A is more equal than 0, 1 to the power 2 f A plus gradient of phi of x transposed dx for the same test functions. So this is something what doesn't work in high dimensions because of this example and the extension by Miller. But if they are the same on 2 times 2, then so what you can do, you can also, if this is too difficult for you over the weekend, then you can also try this one with the transpose gradient. And if you show that this really holds, this inequality, then you don't have a counterexample, but you have something interesting what only happens in 2 times 2 and not in higher dimensions. And if you by chance prove that this doesn't hold, then you are already with the position, because you have a counterexample. So this is what I wanted to say about this counter examples and stuff like that. It's very interesting because the problem can be explained very easily. And it's still kind of, many people have worked on this and no outcome. it's a problem you can only work over weekends, because if you need papers and so on, you cannot spend years and, I mean, if there is no result at the end, then it would be bad. So you can only do it as a part-time. But there are still some positive examples, like that sometimes quasi-convexity and rank 1 convexity are the same. So one example is if you take just quadratic forms, so functions which are quadratic in the gradient. So if f is a quadratic form, if f is m times d, the quadratic form, which means f of a can be written as some matrix M, A dot product with A. So now this has 4 indices, this M, for some M. And so this is a matrix which has 4 in ij, kl. No, so you know what I mean. I don't want to now specify of all these indices, because I would be confusing maybe. So you take something like that. So F is rank 1 convex. So first of all, it's a smooth function. So I mean, you can use this Legendre-Hadamard condition if you want to calculate, if you want to check whether this is rank 1 convex or not. If and only if f a dyadic b is bigger or equal than 0 for every a in R M and B in RD. So that's easy. So you just put the rank 1 matrix, and you have to check that this is positive on the row. So if we ask about convexity, then it would be, it has to be, here there would be a general matrix, which means the quadratic form has to be non-negative. This would be the condition for convexity. But here it is enough that it's like that. So for example, if you just think about the determinant in the case 2 times 2, if M equals D, and this is 2, so FA is a determinant of A. Is it rank 1 convex? It should be, so it should satisfy this. And really, this is a rank 1 matrix, so the determinant is 0. So then it's even true that it's also true for F minus determinant. So are both They are both rank 1 convex, and we also know that they are both polyconvex, for example, because it's still minus determinant is a convex function of the determinant. So in particular, what we know, if you take this 0, 1 to the power 2, and you calculate the determinant of grad phi of x plus f, and phi is W1 infinity function, 0 on the boundary, say 0, 1, 2 to R2, but it works for any dimension. So this is just determinant of f, because the measure, Lebesgue measure of this square is 1. So this shows that only boundary values do matter if you want to evaluate the determinant. And you have affine boundary conditions. So this is a rank 1 convex function. And now if you want to check quasi-convexity of this quadratic form in general dimension, you plug here a gradient of phi, and then you go to Fourier analysis, and you get a Plancherel formula, which would tell you that the Fourier image of the gradient is a rank 1 matrix. So you get something which gives you a rank 1 matrix here and here, always. And this tells you, because this has to be positive, then if you have quadratic form, then you have also a quasi-convex function. Then rank 1 convexity is equivalent to quasi-convexity. If you are in the case 2 times 2, then it's even equivalent to polyconvexity. But there are quadratic forms in 3 dimensions that are rank 1 convex, and it means quasi-convex, but not polyconvex. So then again, everything separates. Yeah, so these are the basic problems. And I think maybe I stop now because I wanted to show you some example which is also related to Schwerak, but I don't think it would be enough time for that to do it, because it's quite some drawing and so on. But it also, finally, the hope would be to get a function that we can distinguish all notions of polyconvexity, quasi-convexity, and rank 1 convexity. So that we construct a function, a different one than Hilbert da Coruña, that we can distinguish the notions of convexity. Yeah. So have a nice weekend and see you on Monday, hopefully.